Good evening. I thank the organizers for inviting me and asking me to give a talk on the 30-meter telescope project. I thought it was a plenary talk, so I put the India's contribution as the main factor, but it turns out that it's a public lecture. So I would give an overview of this project, ambitious project, as well as, of course, India's contribution, as well as the current status of the project. Thank you for coming and attending the talk. I'm Annapurni Subramaniam. I'm the director of the Indian Institute of Astrophysics. And the Indian Institute of Astrophysics is one of the PI institutions in the India TMT project. So there are 3 PI institutions from the country who are majorly participating in the project. So it is not me, the PI, but the institution as the head of the organization as the PI. So I just want to clarify that. So the TMT stands for the 30-meter telescope, and the 30-meter telescope international observatory consists of these consortium. So the Caltech, the University of California, Canada, NOJ from Japan are also participating with funding, the initial funding coming from the Gordon and Betty Moore Foundation, and China was initially participating a part of it. Right now, they are not contributing to it. So these are the current members, along with India. India has 3 PI institutions, and the government of India is participating through these organizations. So this is the picture of the telescope. I mean, the graphic shown here, which is basically a huge segmented mirror telescope. So the logo out here stands for hexagonal segments. So this is a segmented mirror telescope, which is basically actually the primary. And then you have the secondary, and then the tertiary comes over here, and then the instruments are mounted on the side. So the instruments are actually on the ports, which are actually stationary because the instruments are very huge. So the scale of this is like a football field. So it's a very big, I'll come to the details of this project. What is the new era of astronomy with the mega optical and infrared projects? It's not only the 30-meter telescope project which is going on. There are 2 more of them which are in the mega scale. Or the one is the 39 European Extremely Large Telescope. You probably are more familiar with that, ELT. European Union countries are making that. And this is the 30-meter telescope project. These are 2, all 3 are segmented mirror, including the Large Magellan Telescope. The difference being the 39-meter and the 30-meter have segments of the size of 1.4 meter. On the other hand, the 24.5 meter has the larger 8 meter segments. Now, let me ask you a question like, if you want to go from smaller telescopes, optical and near infrared, to bigger telescopes, how do you go? So if you want to make smaller, for outreach purposes, your lenses are basically, it's not mirrors, it's lenses. So you have a tube, you have a lens, and you look through it, you see the object on the other side. But when you start making the bigger telescopes, then you can't make lenses because they become very heavy and they have chromatic aberration. So you move from lenses to mirrors. So you have a collecting area, and then the light comes to the other end where it collects the focus. Either you put the instrument out there or bring it down, the Cassegrain focus. So that is when you go to the reflective optics from refractive optics. Now, how big can you make a single mirror? Can you make it 30 meter? No, it's not possible because it is quite fragile and can break. So there is a limit beyond which you cannot go. So it's typically about 8 meter. You cannot go beyond making a single mirror. So does it put you at the limit of making a optical infrared telescope? No. So you can go bigger by making a segmented mirror. So segmented would mean that you can have circular patches, but you can't, if you put all the circular patches together, then you'll have gaps. So that's not efficiently managing the surface area. So you make it into a honeycomb structure, so hexagonal segment. So I'll come to the picture of it, but when you go to larger telescopes, you move from single mirror to multiple mirror. So it's a segmented mirror technology. So all three adopt segmented mirror technology. But the question is, would you go with 8-meter class, multiple of them, or small 1.5 meter, large number of them? So the first two projects adopt the 1.4 meter, multiple, very large number of them. For example, 30-meter telescope has 492 segments. Now, there is a legacy for it because if you look at Keck telescopes, Keck 1 and 2, they are 8-meter class segmented mirror. On the other hand, if you look at Magellan telescope, they are going for a very new kind of a structure with 8-meter class. This is not proven yet. So this is the first of its attempt in the case of Magellan telescope. So just want to give you the feel of what happens or how there is a breakthrough when you want to go from smaller segmented size, the mirrors, to larger telescope sizes. So these three were in the making in early 2000, and then by end of 2000, like around 2006, 2007, all the three projects approached India. And one thing I should also mention that these are humongous projects which require technical, financial, and different kinds of support, scientific support across the world. So one nation cannot build such huge projects. It's usually a multinational project, and they will always look for partners, and huge number of components have to be made, integrated, etc. So all of them have international and multi-country participation involved. So India joined TMT in around 2010, we had an internal committee. We decided to participate in the 30-meter telescope project, the India. The reasons being, we had a guaranteed in-kind participation. Like, a country wanting to participate has clearly an idea of where exactly they can participate. Guaranteed observing time, technology heritage with partnership based on kick and scalability. Like if you want to make it smaller or bigger, you can do it. So with this in mind, we started participating in 2010, but then the actual international agreement was signed in 2013. And we have already completed 10 years, and we are actually into the second phase. But where is the project right now? I'll come to it. So this is the schematic, which shows that there is a laser guide system which is shooting up for an artificial star for tracking. That is the adaptive optic system. Now, what is the 30-meter telescope? The 30-meter primary mirror consists of 492 segments of 1.44 diameter each. So you can see that this kind of a honeycomb structure here. Each segment is of the size of 1.44. And of that, 492 are there. And it'll provide an ultimate resolution, which is about a factor of 3 better than the current telescopes and 4 times better than JWST space telescope. The TMT will also have the seeing as well as the adaptive optics, which gives you better resolution than the current larger telescope. Now, what do you mean by seeing and adaptive optics? Is because if you have a ground telescope, you are kind of limited by the turbulence in the atmosphere. So if the atmosphere is turbulent, then your image quality will be limited by the turbulence in the atmosphere. So you can correct for the turbulence using an adaptive optics, which would mean that the turbulence, you can measure the amount of turbulence and correct for it by online, is like in the real time, by passing it through a deformable mirror. So you correct the deformation the wavefront has sensed by passing it through in real time so that you get the sharpest images. Now, you cannot do to a very blurred image, but you can do to a relatively less blurred image. So one has to look for sites which are extremely good and has little less blurring. So that's what is required here. But at the same time, you will also have time in the sky night when the blurring is happening. So what do you do at that time? There would be instruments which are seeing limited. It's called seeing limited. But there are instruments where the turbulence is less. You correct for the turbulence and get extremely good image. That is when it can beat the space telescopes. Because the space telescope doesn't need to do anything because there's no turbulence out there. But here you can actually correct for the turbulence and get the resolution which the optics can actually achieve. So diffraction limited achievement of that large aperture can be done if you have the adaptive optics. So there's a technique where you actually shine a laser, find the turbulence in the atmosphere, and correct for it in real time. So that's a complex technology, but it is doable. It has already been used. And that is exactly used for imaging the exoplanets, etc. So major science goal being the direct image of the exosolar planets and study of extraterrestrial life, because actually you can resolve them and get their spectra to see what kind of signatures these planets have. Study of first stars and nucleuses at the beginning of the universe, as we can see that the James Webb Telescope is already able to see much into the early universe, and with the faintness, you will be able to see these stars and identify the spectroscopically identify what has been the signatures of the first stars, and the dark energy understanding evolution of the universe, which requires the understanding the space-time curvature and using weak lensing, etc. So these are the main goals. One is this is the exosolar planets being the near universe science goals. This is the mid, and then this is the cosmological time scale. So these are the main drivers, but there are a lot more of them which can be done with the different instruments. Now, how are you going to be building this humongous structure? There are participating countries contributing to various things. So the USA is doing the civil works. It's supposed to come up in Mauna Kea, and they also work on the integration instrument and all the major the integration is the engineers and the team which actually integrates the contribution is in the US. Canada is actually contributing to the coyote type dome, because this dome is very huge and it has to withstand the wind. So it's at a very high altitude of 4,000 meters above sea level. So there'll be a lot of wind, and the wind should not be shaking the structure. At the same time, it should not create a turbulence, but let it go, because it has to thermally be, thermally in equilibrium with the surroundings, because you can't have heating or cooling taking place, which can actually create turbulence. So this is a complex structure. The Canada is taking care of it. Japan has the telescope structure segments and all the 492 blanks. When you come to mirror, what happens is you start with a blank, like, a flat mirror, thick slab of mirror, and then you polish it to the extent of curvature you want and then coat it. But the blank, the flat glass pieces are coming from Japan. India has the responsibility to polish making the curvature of about 100 segments, coating of all the segments, and as you can see, if you have 492 segments in which is supposed to act like one single surface, one single meniscus, you have to support them very carefully. They're called segment support assemblies. So all the 492 segments will be supported by segment support assemblies that's going to be made in India. And when the segments come closer or farther away, you need to figure out whether they're not colliding, right? So the edge sensors. So edge sensors keep track of how far or how close they are. And that's a pair. Each will have 6 pairs. And actuators, which can move up and down. Like when the telescope is up here, there would be some gravity, but if you're looking at an object out there, the entire telescope tilts. So the gravity changes. So you have to actually support it to make sure that the meniscus remains the same. So the complex, I'll come to that. So that's below it is called the segment support assemblies. They're all coming from India. China has tertiary mirror and laser launching system, but this is now being taken by care by Canada. So that's what I'm saying. So you have this segment. So of this 492 segment, one segment will look like this. So you start with a circular mirror, and then you configure the surface and cut it into a hexagonal. So, and then the below is all the segment support assembly. And then you also have electronics, because you're all electronic control. You need to get the voltages, power, etc. And these are the edge sensors which are fitted onto the edges of those mirrors. Actuators will push it up and down. And we also have software and science instruments. So these are the kind of entire set of contributions which are coming in. But you can also see that in the software, each segment will generate a lot of data, metadata, to make sure that everything is functioning. How do you know that one component is lost or misbehaving? So it would not make the entire meniscus correct. So this software backbone communication system has to collect all this data, which will be generating data at various time steps. one component would be generating in 1 hertz, something will be in 10 hertz, something in 100 hertz. So everything has to be collected together and information to be passed on. So that is the software, one of the software requirement, as well as archiving all the metadata, science data, and the pipelines. Um, so giving the more, so who makes this? The PI institutions are research institutions. So we can only do the designing part or understanding the implications to the science. So we have to deal with a lot of industries. So industries have to generate, get all this manufactured. So when you go and talk to people, the industry has their own language, their own way of working, but we have been interacting with them for the last 10 years or so and qualify them for the purpose. So most of these components for the TMT, the initial prototyping is done at GPL. Now, if you do a prototyping of a complex instrument in a laboratory, the technique which you use will be very specialized and which will not be transport or can't be used in an industrial environment or in a mass production environment. So we have to do prototyping in the industrial scale along with validation of the manufacturing processes for each of them. So this has been done with a team of large number of engineers hired for the project and the know-how to be transferred to the industry as well. So we have managed to do it in the last 10 years or so, which requires very high quality checks, very high, systematic, each piece to be checked and measured and at various temperatures. So quality checks and process controls are vital here. So we have transferred the technology as well as the know-how to industries as well. So many of them are participating. Now, overall projects of the 492 segments, 300 segments are 336 blanks are already fabricated, 60% complete. This in Japan. And the Japan, India, and the US are already polishing. Ohara, Japan is currently qualifying the furnace for the remainder. Because when you have making this in the furnace, just the flat blanks of the mirrors, that itself requires, the furnace has to be requalified, etc. Now, polishing is 103 roundels is polished. So this is the one roundel. So you polish it and then you have to hex cut it. Now, this is polished using a technique called, say, the stress mirror polishing. So it is also, it's a curious thing. How do you polish a mirror? You have a flat thing, you grind it and remove the layer on top of it. So normally you sit and grind and normally telescope workshops do that, right? You do that. But it takes a lot of time because you grind it, you have to check whether you're ground properly or not. Enough material is taken away, and the curvature is taken, come out or not. So it's a very iterative process. You grind it, check it, grind it, check it. So it takes a lot of time. So the rate at which we have to produce is about one segment in 2 weeks. So this kind of a process is not possible. It's not going to give you, the telescope will come in another 50 years if we use the same process. So in the case of the stress mirror polishing, what you do is, it's also the surface you have to achieve is also complex because generally spherical surface is axisymmetric. You can do this and then axisymmetric, you get it. But if it is not axisymmetric, it is actually off axis, then you have some weird shape. It's not centric, it doesn't have a center, and the ellipticity is also the same. So how do you do it? You can take mirror as a liquid. So you stress the mirror. So put a stress to the sense that you can do an asymmetric stress because if it's not axisymmetric, right? Asymmetric stress and polish it to a spherical polishing. And you release the stress, leave it on a buy-off station for 24 hours. The surface will regain the shape of the stress you have applied. So it's a very careful technique. You need to stress it appropriately and leave it, and you will get it. But one has to have this particular machine which actually creates all the stress. And then you have to have an interferometric machine which actually measures the surface configuration. So we have achieved it, and then this is already, we already qualified the process. So we actually achieved it in 10 days, one segment. After that, since you're doing the stress mirror polishing, you need to have some kind of symmetry. So you can't cut it before polishing. In the case of web mirrors, They were actually hexagonally cut, the beryllium mirrors, and then polished. But in TMT, you can't do that. So you have to first polish it and then you hex cut it. That's another complication. So we have already completed 2 by India in the case of TMT. Rest of them are going through. The tertiary and the secondary mirrors are also being manufactured, and the work is in progress. Belgium is involved in that, AMOS. And the machining, which is the hex cutting, this is also very, very complicated stuff, because once you have polished and you're cutting, there's not be any stress transferred onto the mirror. It's very, very highly complex technology. We are also qualifying in that. And the segment support assembly is already qualified by Larsen and Toubro. And this is being, Bob Krishna is checking this. So this is already in the TMT office for integration in the Monrovia lab. We also have control systems, that is the actuators and other electronics, etc. That is also being qualified. So we are working with about 70 plus industries, which are all contributing to the various causes of it. Now, software is, as I said, we have observatory software controls and telescope controls. The instrument control and data management are part of it. And we have delivered some part of it, but right now the software is paused because the project is getting delayed. So we are on the pause. So coming to the tentative construction, we expect to start by 2025 and operation to begin by 2035. These are the first instruments, WFOS, Nefarious, Iris, and Moody's. I'll come to the details of it. And the second generation instrument is also there. You can see the humongous size and the person standing there. The instruments itself is like a small room size. So the instruments are very, very heavy as well. So these are the narrow field infrared adaptive optics. The adaptive optics is considered as it's not an instrument, but it's considered as an instrument because it's very essential for images which are coming from IRIS. IRIS is the one which is going to look at the things like the galactic center, looking at microarcsecond motions of the stars. So to get the actual motions around black holes, etc. WFOS is a wide field optical spectrometer, which is a seeing limited spectrograph, and diffraction limited high resolution infrared spectrograph. MODIS is also being planned. This is the first decade instruments, which is actually going through different revisions because the landscape into 2030s is changing because of Webb and various other Euclid, etc. WFOS is going to go up, but the high resolution spectrograph is the one which is moving forward now. And the planet formation instrument right now is called PSI. So these two are moving forward. So you want to compare the capabilities, you look at with TMT with AO will be actually looking at very high angular resolution and also at various wavelength ranges. So you can actually see 25 kilometer on Jupiter. So 10 AU at 100 parsec. So you can actually see a 1 kiloparsec at Z equal to 1. So, et cetera, these limitations. So this actually gives you high angular resolution because of adaptive optics. And it's very important that the site which actually can support adaptive optics is chosen to clearly get the spatial resolution. So the resolution is coming because not only because of the D, but also because of the AO. So AO actually makes it into D4, not into D square. So these are the, I mean, if anybody wants, I can go through it, but I'll just skip it. Oh my God, okay. Sorry. This is the previous instruments. Somehow this is not coming properly. So this is the WFOS. India is quite involved in the wide field optical spectrograph. This is the high resolution spectrograph, which is the second decade instrument. There are, how do you do science and how do you develop science goals? So it's not only about the partners developing science goals. There's an international science development teams involved in TMT, which is where a science, anyone interested throughout the world can participate. They're part of the international science development teams. They are in these kind of categories. So you have 8, 9 categories. And 2014, the first ISDT, the science document came out. But now there's a revision happening because of the landscape change. So these are the conveners of this ISDTs, and the announcement for the next opening of membership to ISDTs will come in a few months' time. So if you're interested, you can join any of the teams and participate in the science development. Civil construction of the site is stalled. It's tried to start in 2014 and again in 2019. Both times it is standoff because the Mauna Kea mountain is considered as it's a site where the locals consider it to be very holy, and construction over there is not very they're not very proactive supporting that. But there have been attempts to uh, I mean, give them in the sense that get a understand the demands of the local people, and also to get a okay from the population. It's basically that there has been the local population has been finding it difficult to understand that many things are being done without them getting any benefit out of it. So actually, the locals benefiting from the project and also being part of it, and them being part of the key decision making is very important. So that has now changed, and they have made the government of Hawaii is making the astronomy as a state policy, and also the stakeholders of the Mauna Kea land is done by a stewardship oversight authority, where the registration is done not by the University of Hawaii but by the representation of the local native Hawaiian and local population, which would mean that what happens with the mountain, they have a say over it. Previously, there was not. So we are working with them and trying to see how we can help the community, at the same time help astronomy as well. So the National Science Foundation started an environmental impact survey for two sites, Mauna Kea and La Palma. So the actual site number one is Mauna Kea, but there is a backup site in La Palma. The La Palma Mauna Kea comparison is shown here. The main thing is the altitudes are like, the Mauna Kea is at 4,000 meters above sea level. La Palma is 2.2 kilometers. And you can see that the isoplanetary angle is higher in Mauna Kea with respect to La Palma, and the coherence time is higher here. So these parameters are important. The first two parameters are important in making sure that the AO works for most of the time, so you can get a high angular resolution. And in water vapor content is, so the 54% of the time is less than 2 mm in Mauna Kea, which will help in infrared. In La Palma, it's only 20% of the time you have water vapor less than 2 mm, which would mean that you have absorbency of the infrared through the atmosphere in La Palma. So these are the comparison, but of course, Mauna Kea is the preferred site, but La Palma is the second site in case things don't work out in Mauna Kea. There's also an attempt to remove the older observatories from the top of the Mauna Kea. You'd have seen the recent news that the Caltech sub-millimeter observatory has been fully removed. So you can actually making space, because you're not making more and more structures without removing the unused ones. So that is also going on right there. The another development which has taken place is that the National Science Board, which is the governing body of the National Science Foundation, has given an instruction that they've recommended to limit the NSF support to 1.6 billion, which would mean that one of the projects, that is the either the TMT or the GMT, will only be supported. So I just want to give you a thing that of the three projects I said, ELT is the European one, so European Union is supporting it. But there are two projects which are coming from the US, the GMT and the TMT. Now, earlier there was an attempt to fund only either of the two, but then the US community came together and said, let's have a presence in the north through TMT and in the south through GMT. So it's called the US Extremely Large Telescope Program by funding both. So Astro Decadal Survey actually supported both. That is the US ELT program. But then it would mean that huge amount of funding. So the NSB has said that you actually fix the funding to 1.6 billion and then select one of the candidate projects. But there's also been the House of Representatives, senators saying that no, you should fund both the programs, because US has been the leading in the astronomy area, and US should not leave the actually that position of leadership. So right now there is an advisory committee which is formed by the NSF, which is actually going to take stock of the situation and then give its advisory to the board and the NSF by September. So we're waiting for that to happen so that we know which stage it will be going further. So again, so these are the things, and we have actually taken the NSF, the final design review with NSF again, but we will wait for the advisory committee's recommendation. So right now the position is getting on hold, and we expect to start the construction somewhere in a year or so from now with the site preparation, and we expect to see the early operations by another 10 years or so. So this is the timeline for it. And that's all from my side. Thank you. Any questions? Comments? In? Yeah. So these are the sites. India is a partner, but then the location of the telescope is here. It's not going to be in India. Yeah. It's going to be in either Mauna Kea or La Palma. Yeah. It's not going to be in India. Yeah.
So I don't actually understand very well this adaptive thing. Like I understood that you send a laser, and with that you can trace how is the turbulence on the atmosphere. But I mean, I imagine that this laser has to, be reflected so that you get a signal back. And where is this reflection happening?
Yeah. So you basically launch let me go to one of the pictures. So you launch the laser from the top of the telescope, and you get the beam back. And yeah, so let me say, okay, there's no enclosure here. Yeah, okay, yeah. So this is you launch the laser from here, this particular thing. So you go, bring it down, and then you would actually, you see as a star. The laser launches and sees as a star. And then for you, it's as a point source. But when you measure it in the instrument, it will be actually a spread one. So that wavefront error can be, you can actually have it in the same frequency range. You can put it through a MEMS kind of a thing where you can, if it compensates for the wavefront error on real time. So if you can say that the wavefront is distorted by this, you actually do the opposite thing, so that you get a flat wavefront. So, but this has to be done in real time. So this is normally done in K-band, and then you actually can fold it in. So adaptive optics is actually using this to feed into the instrument. So the beam is first fed to the nefarious, and the output of that, which is actually corrected for the wavefront, is fed to iris. So you get sharp images. Is it out? Yeah.
Then Yeah, sorry, this is very outside of my field of knowledge, so it's why I'm also so curious. But that is a quite small column of hair, right?
So
compared to the entire atmosphere.
So basically, you do a sodium laser. So in the layer where the ionosphere is there, where the sodium, that ions reflects that back. So it actually acts like a middle layer where it acts like an artificial star.
Okay.
But you have to use that artificial star very close to your object. So your column which you're looking at, the atmospheric column which you're looking at, is very close to your object, so that the correction which you're making based on this particular laser guide star is applicable to your the object. So this is a very simple technique, but there is you can have multiple laser guide star and then correct it together and then make it a little more. So the multi-conjugate adaptive optics is like that. So GLIO is the single one. Multi-conjugate has more number of things. So you can actually have it in a much complex way. Yeah. This is a very, very rudimentary explanation.
Thank you.
Any other question, comment?